Welcome, fellow communications and electronics geeks. I just wanted to tell you about a new type of part that I just came across. Thermal jumpers. What are they? What problem do they solve? And what are the pros and cons of using them? Let's get started. Many hobbyists and low-volume manufacturers design using custom PCB boards fabricated by a number of PCB houses, such as OSH Park and PCB Way. This discussion assumes that you are designing your own PCB board, and you have used surface mount parts before. It's not exclusive. Thermal jumpers can be used for point-to-point wiring also. It's just that they're easier to use on regular PCB boards. So what are thermal jumpers? They are surface mount parts that have a piece of insulating ceramic between two terminals. The ceramic has very low thermal resistance, but has very high electrical resistance. There are two manufacturers of thermal jumpers: Vishay, which uses the name Thermowick, and American Technical Ceramics and AVX under the name Q-Bridge. These parts are currently carried by both DigiKey and Mouser. So, we have a block of ceramic on a surface mount board. What on earth will we do with it? Well, let's look at a common design challenge with a low dropout voltage regulator. Suppose I have a 9 to 12 volt supply that I want to regulate down to 5 volts. The load is 300 milliamps. So the worst case power dissipation in the regulator is 2.1 watts. No problem. I select an LM317 in a TO220 package. Add a cap on the input and the output, and we're done. I'm sure you've all done this 100 times. 2 watts is a bit much for a TO220 package. The junction to ambient thermal resistance is about 38 degrees per watt, so the regulator will go up to 105 degrees Celsius. That won't kill the part, but on a warm day, you'll be pretty close to thermal shutdown. Not the best design. So we really want to redirect the heat to somewhere else on the board or into a metal case. Your first reaction is to bolt the tab of the TO220 to ground. Nope, you can't do that. The tab of the TO220 is connected to the output of the regulator, not to ground. So you start looking at alternate ways for getting the heat out. You can do a stand-up heatsink or a copper pad on the PCB. But what if there was a different way? If we attach a thermal jumper between the tab of the TO220 and ground, assuming the case of the product is ground, then we solve two problems. The output tab is now electrically isolated, but the heat goes through the jumper to the case where it is dissipated into the air. If we use a 0612 size jumper with a thermal resistance of 4 degrees per watt, then the regulator temperature is now only 33 degrees. Yes, I know, we have to take into account the thermal resistance of the case, but this is really just an example. Let's look at a real-world example. I'm currently working on a new caving headlamp. Anyone who has worked with high-output LEDs knows that the hardest challenge is getting the heat out of the LED. One of the common ways is to mount the LED on the top of the PCB, add a lot of thermal vias from the pads of the LED to the bottom of the PCB, then add a thermal pad between the bottom of the PCB and the post in the aluminum case. It works, but there are a lot of steps for assembly. The new design uses thermal jumpers. The LED driver sends a current through an inductor, through the LEDs, and continues through a sense resistor. The voltage across the resistance is the feedback signal back to the driver, which enables the driver to create a constant current through the LED. Note that the hottest component in the design is the LED, and it's not ground referenced. The worst case power in the LED is 4.4 watts. That's a lot of heat in a tiny 1.6 square package. To get the heat out of the LED and into the aluminum case, I'm using thermal jumpers. Here's the top layer of the PCB design. The headlamp uses two LEDs, one for spot and one for flood. Each LED is mounted on surface mount pads with a large amount of copper. The copper takes the heat to the thermal jumpers. For maximum heat transfer, I have placed thermal jumpers on both the anode and the cathode of each LED, for a total of 4 jumpers. The other side of each thermal jumper is tied to a mounting hole which is connected to the case. It is only fair to discuss the major downside of thermal jumpers: cost. They're not cheap. There are 2 types of material used in thermal jumpers: aluminum nitride and beryllium oxide. Aluminum nitride jumpers are cheaper, but the beryllium oxide has 2/3 the thermal resistance. The 0612 jumpers from Vishay that I am using are 81 cents. That's cheap if you're only using a few, but compared to an 0603 resistor at 1 cent and a ceramic capacitor at about 10 cents, you can see that thermal jumpers are expensive. I'm spending more money on the jumpers than I am on the LEDs. And if you want beryllium oxide jumpers, well, those start at $2 and up to $11. So that's the scoop on thermal jumpers. I don't think everyone's going to run out and buy bags of them, but it's just another tool in your electronics toolbox. I would love to be able to say that I personally tested thermal jumpers and I have measurements to share, but at the time of this video, not everything is working on the new headlamp. So that's it for now. Remember the communications and electronics motto: build, go cave, repair, repeat.